just open the morning session. So good morning, everyone. I'm happy to see you back. And it's my great pleasure to introduce the first speaker of this morning. Well, introduce. I mean, I read it. Everybody knows Satya. Mr. Satya Majumdar from University Paris. And he's going to explain us about dynamically emergent correlations. Please,
Thank you, Albert. Thank you very much for the introduction. And so let me start by thanking Sanjib for the invitation and also to RRI for the hospitality, because I'm spending a month over here. And it's always a pleasure to come back here. So I'm going to talk about this dynamically emergent correlation. So this is a subject on which, we are developing this subject a little bit over the last couple of years with many friends and colleagues, and many of them are present in the audience. Gregory, Manas, Sanjeev, Urna, who else? Arnav, and Nikhil, and many others whom I'll acknowledge at the end. And so if I may just summarize in, just a few sentences what the talk is about. So this is about the following. So basically what I'm going to show you is that we found a recipe, sort of very simple recipe, to construct a sort of, strongly correlated non-equilibrium stationary states for a bunch of particles which are driven out of equilibrium. And this drive, stochastic driving, is actually sort of motivated or inspired by stochastic resetting that Somrita introduced nicely yesterday. And in fact, but the nice thing about this is that usually, if you have a strongly correlated system, gas or particles, it's very hard to, even if you know the joint distribution of the particle positions in the stationary state, it's very hard to compute any physical observables in general. The biggest example is the random matrix theory, the eigenvalues. So it's very hard, but nice thing about this particular set of models is that there is a particular structure in the joint distribution of the stationary state that allows us to compute several physical observables explicitly, and they have quite non-trivial results. Okay, so in other words, in short, I mean, basically, we found a sort of recipe to construct a whole class of solvable, strongly correlated systems. Okay, that's the sort of main summary. Okay, so let me, so here's the outline. So I'll first tell you what I mean by dynamical emergent correlation and the general setting of it. So essentially, these particles are independent, and they are, they share a common environment, which is stochastically fluctuating. So that's the general setting. And a simple example is this switching confining potential, which could be a box or a trap. And I'll then show how to characterize the exact non-equilibrium stationary state. And it has this, as I mentioned, it has this, very nice mathematical structure, which is called the conditionally independent and identically distributed, which allows us to compute several observables exactly. And then I'll talk about the recent experiments using optical tweezers done in the group of Sergio Celiberto at École Normale Lyon. And then, I will talk about some other models, both classical and quantum models, where you have the similar CIID structure, and then I'll summarize and conclude. Okay. So what's the general setting? Okay. So imagine that you have a bunch of particles, and for simplicity, they can be anything, but think of them as just Brownian particles. And they are completely non-interacting. Okay. So there is no direct interaction between these particles, but they're coupled to some environment. And the environment is stochastically fluctuating. And the particles are completely slaved to the environment, so the particles do not affect the motion of the environment. I'll give you an example in a minute. This is a schematic picture. This red is something environment, so you can think of a box which will increase the size and things like that. So these guys, the environment motion is completely independent of the particle motion, but the particles, they do, share the same environment. And if this environment stochastically fluctuates, then that generates correlations between the particles. So that's the sort of general, stochastic dynamics, stochastic is important, and the shared environment, that's important. So that induces very strong correlation between particles, okay? So this is what we call the dynamical emergent correlations, and I'll give you an example in a minute. So this is somewhat reminiscent, but not exactly same as the famous, the Huygens pendulum. So Christian Huygens was a Dutch mathematician in the 17th century. But he was also a very expert clockmaker, okay, in Europe. So, once he was sick at his home and he was just doing this experiment. So he put two chairs like this, and he put a wooden beam across the top of the chair like this. And then he hung two pendulums from it. These pendulums, there is no direct interaction between these pendulums. And then you just give a kick to one of the pendulums. So then you see that the other pendulum in the beginning, it doesn't move at all. But then after some time, transient time, this pendulum starts moving, and eventually they get completely synchronized. Okay? So even though there is no direct interaction between them, there is some correlation which is being generated. But in this case, the mechanism is that this guy, when he starts moving, it affects the beam, and the beam in turn affects the other pendulum. So here actually the particles are actually affecting the motion of the environment, if you like. So this is different from our setting where the particles will not affect the motion of the environment. So it's a more dramatic even. It's just that they share the same environment. Okay? And that will introduce strong correlations between them. So let's look at a particular example. So this is a simple example you can think of doing a Gedanken experiment or actually do the experiment. So imagine that you have a bunch of particles, and for simplicity, let's say just overdamped Brownian motions with reflecting boundary conditions. So they're in a box of size L1. And then this box, you just, imagine this is like a piston. You go from L1 to L2 with rate R1, and then reverse rate R2, you go to L2 to L1. And when, if your particle is here, it just gets pushed by the wall to the wall location. And so basically what it means is that, just this. So the environment is just, size of the environment is fluctuating between these two values stochastically. But the particles there is no interaction between them. And then you ask, so essentially the model is very, very simple. So you have the L of t, which is a stochastic variable now. And it's a dichotomous variable. It takes values L1 up to an exponentially distributed time, which is distributed exponentially as R1 e to the power minus R1 tau. And after that, it switches to value L2. It stays up to an exponential time with parameter S by R2, and then it switches back. And so it's a dichotomous process, the size of the box. And the particles are just doing their Brownian motion. Okay? And if they hit the wall, it's reflecting boundary conditions. Yeah.
So if you suddenly compress
yeah.
what happens to the particles in between?
Yeah, so that's what I said, that they stick to the wall. I mean, you can model it in any way you like, but here, I mean, the simplest thing is to just think of the stick to the wall. Okay? And then the goal is to compute the joint distribution of the particle positions at time t. Okay? And in particular, if there is a stationary state in the long time limit, we would like to know what is the stationary state and what is the nature of correlations between the particles. Okay? So it's just only correlation, source of correlation is that they're sharing a common fluctuating environment. Okay? So now this problem is actually, it turns out to be quite difficult. I mean, we haven't been able to solve this problem. But I'll first focus on a particular limit of this problem, which is itself is quite interesting. So this limit is, imagine that L1 is 0. So that means you squeeze the particles to the origin, and L2 is infinity. That means, you take this particle, the box, you go to infinite. So that means it's a free space, diffusion. And then, after some exponential distributed time, you just squeeze them all back to the origin. Okay? And you also set R1 to be infinite. R1 means that, after you squeeze it, instantaneously, you release it. And R2 is some R. So basically, essentially, up to an exponentially distributed term with parameter R, it's just doing diffusion. And after that, you reset all the particle positions back to the origin. And then again, you go. So this is the classic resetting problem of n particles that Shomrita was talking about yesterday. So you see that, imagine that all the particles start at the origin, and then, let them diffuse up to a, random exponential time distributed with the parameter R. And after that, you squeeze the L back to the origin. So they all get pushed to the origin. And again, you instantaneously release them, and they do diffusion and so on. So this is the, this is example in d equal to 1, but you can do it in any dimension. Yeah.
R2 is also infinite?
Yeah, R2 is infinite. That's what I said. No, R2 is not infinite. R2 equal to R. R2 equal to R.
Squeeze it slowly?
No, you squeeze it instantaneously. You let the box to be infinite up to an exponentially distributed time, and then you instantaneously squeeze it to the origin and release it.
So what is R1, R2?
R1 is the rate at which you go from L1 to L2. R2 is the rate you go from L2 to L1. Okay?
It's the rate of deciding when to go, not the rate of not the velocity.
No, rate. That's what I mean. If you look at this, I mean, this is the problem. I mean, Yeah, L of t is just the dichotomous process. I mean, I can control this any way I like. Okay. So this is trajectories of the particles, and so what you want to know. So this is the essentially diffusion of n independent particles with a stochastic resetting with rate r essentially. Okay, and so this is the multi-particle generalization of a single particle case that we had looked at with Martin long time back, and that Shomrita discussed yesterday in her talk. And so this is just, it's good to think of this as n independent particles in one dimension, but of course, alternatively, you can also think of this as a single particle resetting to the origin in n dimensions. But we'll see actually it's this dual picture of thinking of them as independent particles and think of as a gas of particles is more appropriate in our context. Okay, okay. So this is in this limit already. It's not a completely trivial problem, and let's see what we can say. So just to remind you a little bit about the single particle case n equal to 1, and then we'll generalize. So n equal to 1. So you have just a single particle doing diffusion, and then after some exponentially distributed time with parameter r, you reset back to the origin, and then you just continue this process. So if you're doing simulations, that means in a small interval delta t, you update the position of the particle. X at time t plus delta t is 0 with probability r delta t. That means you reset to the origin. And with the complementary probability, you just do diffusion, so which is just normal diffusion, white noise essentially, with the diffusion constant t. Okay, so that's the model. So r is the only parameter. Now this model, of course, has two different aspects. So one is that what is the non-equilibrium stationary state, and the other is these first passage properties that Shomrita discussed yesterday. So today I'll not focus on the first passage properties. I'll just talk about the stationary state of this problem. Okay. So then so this is a very, very simple elementary problem, right? So you have a PR of xt, which is the probability density to be at x at time t with this parameter r here, and you start from the initial position, which is the delta function, okay? And you ask, what is the position distribution at time t? Okay. So if you don't have resetting, then of course this is just a trivial, Gaussian problem, e to the power minus x square over 4 dt. Everybody knows this. And now you switch on this resetting rate r, and you ask, what is the position distribution at time t? Okay. So this actually you can solve it very simply using a renewal picture, and I want to explain this because this will appear naturally when I generalize to n particle problem. So this renewal equation is the following. So I want to arrive at x at time t. I look at a trajectory, and I look at all possibilities of the number of resetting events. Okay? So it could be that in a given trajectory, there is absolutely no resetting event in 0 to t. So this happens with probability e to the power minus rt, because this is just a Poisson process, right? So in that case, you just have a free propagation from 0 to x, which is just a free propagator here, which is just a simply Gaussian. Okay? So this is the case of no resetting. Now you can have one or multiple more resettings. So in that case, all you need to do is to keep track condition on the last resetting event, because you don't care what happened before that. If you know when the last resetting occurred before time t, which I call this tau interval here, if I know this, then I know that after that there is no resetting, so it's just a free propagation up to x. So this is p0 of x tau. Okay? So this is conditioned on tau. And then tau itself has a distribution. And what is this distribution? You have no resetting in 0 to tau, which is e to the power minus r tau, followed by a resetting event, which is r times d tau in a small interval d tau. Okay? And then, of course, this tau can be anything from 0 to t. So you have to integrate from 0 to t. Okay? So that's it. So essentially, the important point here is that this just you have to identify the right variable, and if you condition on that, then it's it's quite very simple, and you can check that this is indeed the exact solution at any time t if you write down the Fokker-Planck equation, and you can show that this is the exact solution. But I think this is very instructive to look at this renewal picture. Okay? And in particular now, if you take the time going to infinity limit, this term will drop out. This will be 0 to infinity, and it's a Gaussian times e to the power minus r tau. You can do the computation integral very simply. And this is just a double exponential distribution, exponential on both sides, e to the power minus x. And the length scale here, which is square root of d over r, 1 over alpha naught. So this is just the typical distance the particle travels between two successive resettings. Okay? So the stationary state comes here from the competition of the, between two resettings, it is, is diffusing. and then you are resetting from time to time, you are going back to the origin. So these two competing effects drives the system into a stationary state. Okay, so this is the sort of, very simple exact solution. So when you put this thing, you see that there's a cusp at the origin because of this mod x here, and it decays exponentially. So it's non-Gaussian, and moreover, it's a non-equilibrium stationary state, even though it looks like a Gibbs state. It's not, because there is a constant probability current in the configuration space, because by resetting, you are going back to the origin, but there is no reverse move. So therefore, detail balance is manifestly violated. So it's a non-equilibrium stationary state. And so this prediction was verified a few years later in 2022 from the group of Yale Roikman, and both Arnob and Slomi, who are in the audience, they participated into that. And you can see this is holographic optical tweezer experiment, and you can see that it matches perfectly well with the theory. Okay? So this is for a single particle, very, very simple. So now let's move to multi-particle, n bigger than 1. So n bigger than 1 is also, again, very, very simple. You can use exactly the same renewal picture. Okay? So I look at my trajectories, and again, you can see that I can just have to write the joint distribution of all the particle positions at time t. So again, the first term here is the case when there is no resetting between 0 to t, which occurs with probability to the power minus RT. And in that case, since the particles are independent, it's just a product of the individual propagators. And then when there are one or more resettings, you just have to look at the last resetting time before t, because you don't care what happened after that. You know by definition that you are at the origin. So it's a free propagation after that, condition on tau. And then you have to average over this tau. So it's a very simple generalization of the n equal to 1 case. So this is the exact answer of the joint distribution at all time t. And so first thing you notice that, so this is actually sort of work that was done with my PhD student Marco Biruli, who just graduated and went to University of Chicago, Hernan Laralde, and with Gregory, who is present here. And so first thing you notice is that this joint distribution, it does not factorize. Okay? It does not factorize. So that means there is some correlations which is being generated by the dynamics itself. And this point is that if you condition on tau, then of course they are independent. Okay? But the conditioning variable tau itself has a distribution. If you do a sharp restart, like Shomrita was talking about yesterday, so if you do a sharp restart, then of course it'll be delta function, and then it will be factorized, so there will be no correlations. Okay, but for anything that is non-delta function, you will have a correlation generated from this term. Okay, so the point is that the interactions are not built in. The particles are non-interacting between resettings, but because you repeatedly and simultaneously reset them, so that actually generates correlations, and the shared environment here is precisely this last resetting time, which is, so this drive, the common drive of simultaneous resetting, so that is actually generating the correlations between the particles, and we'll characterize that immediately. So this is what we call the dynamical emergent correlations. Okay. So if I want to calculate from this, you have the explicit joint distribution at any time t. So I can, first look at the correlation function at time t, equal time correlation function between any pair I and j. So clearly by symmetry here, because these are Gaussian, so there's a x going to minus x symmetry. So the normal typical correlation connected correlation function is 0 at all times t, trivially. Okay? So to detect the correlation, you have to go to higher order. Then the simplest higher order correlation function is just this guy xi square xj squared minus its connected part. Okay? And you can compute this because it's very simple computation, because it's just a Gaussian, so you just have to do a integral over that. And you can compute that, and this is just becomes 4d square over r square. D is the diffusion constant, r is the resetting rate, times some function of the scaling function of RT. This is the dimensionless time. And this function is very simple. It's 1 minus 2z e to the power minus z minus exponential minus 2z. So if you plot as a function of z, it actually grows like z cube in the beginning, and then it saturates to value 1 at z goes to infinity. So it goes to a non-trivial constant at long times, indicating that even in the stationary state, you'll have a residual strong correlations between any pair of particles. Okay? And this is the dynamically growing correlation, essentially. All right, so now if I'm interested in the stationary state, so I can take the t going to infinity limit. So the first term will drop out, and you just have this integral here. And so therefore, this is the exact stationary state. Okay? And again, you see that the correlation here, condition on tau, they are independent, but then you have an average over tau to do drawn from the exponential distribution that actually correlates these particles. And this is an attractive all-to-all correlation because the correlation function is positive. Attractive because simultaneously you are pushing them all together towards the origin. That generates an effective attractive all-to-all interaction between the particles. And it's strongly correlated in the sense that there is no finite correlation length beyond which it becomes uncorrelated. They're all fully connected. They're all completely strongly correlated. Okay? All right, so and then now you see that this joint distribution in the stationary state has this particular structure. So it's like there's a conditioning variable which has a distribution h of tau is r e to the power minus r tau. But otherwise, they are independent. It's just, correlation comes from this extra averaging over this conditioning parameter u. Okay? And that's why we call it conditionally independent and identically distributed. If I fix u, then this is like an ideal gas of particles basically. Okay? So and the ideal gas, we know everything, and you can compute everything, and then all you have to do is to average over this h of u. Okay? And h of u in this case is just simple exponential. Okay? So yeah.
There must be a correlation length, right? I mean,
there is no correlation length. I mean, because
from
everybody is connected to everybody else. Where is the correlation length coming from? For any pair of particles is exactly same. Okay, we can discuss this. All right. So, oops, sorry. So now the point is that even though this is not factorizable and they are strongly correlated. So you can actually compute because this particular structure is very nice because it's solvable because all you have to do, despite the strong correlations, you can calculate several physical observables. So for example, all you have to calculate is for ideal gas with tau as a parameter, and then you have to average over this parameter drawn from this whatever distribution is. Okay. So the first step is to compute for IID variables, which is the ideal gas, and then you have to just average over this random. These are two steps. Okay. So I will not show you the details of the calculations. Now, what are the physical observables? So first thing to ask is, you have a gas of particles, let's say in one dimension, and first thing to ask, it's an inhomogeneous gas. Okay, the density is not constant. So you can ask, what is the average density profile? Okay, so that's a very global observable. And then you can ask for local observables, like for example, you can take you to the microscope and look at a configuration of particles, and you ask, what is the distribution of the rightmost particle? You order these particles, and then you ask, what's the distribution of the rightmost particle? Okay, so this is called the order statistics, or the kth rightmost particle. You can ask for the gap between two consecutive particles. Okay, what is the gap? What is the distribution of the gap? You can ask for the full counting statistics, which means that I take some interval, let's say minus L to plus L, and I ask how many particles are there? What is their distribution? So these observables are motivated from random matrix theory because, in random matrix theory, people study the statistics of eigenvalues of a Gaussian ensemble, for instance. And there, the name of the game is knowing the joint distribution. You want to calculate several global and local observables, and they are quite non-trivial. For example, average density in the random matrix case, it will be Wigner's semicircular law for Gaussian ensembles. If you look at the maximum, let's say the rightmost particle, this is the Tracy-Widom distribution. Maybe you will hear from Kazumasa's talk later. And then there is this spacing distribution between particles, full counting statistics. All these things have been studied for ages in random matrix theory, and they are quite hard to compute in general. Okay? But here in this simple example, because of this particular mathematical structure, CIAD structure, one can calculate all these observables quite simply, and they have quite non-trivial properties. So I just flashed through the main results without spending details, but details is there's nothing much to do basically. You just do it for ideal gas, which is very simple, and then you just have to average. Okay? Yeah.
Does the particle resetting happen independently for different particles?
Yes, then they remain independent at all times. Yeah. All right, so let me just show you some explicit results. Okay, so first is the average density profile. So average density profile is very simple. Yeah.
And this thing will disappear if you will reset not all of them simultaneously, but one by one at random.
No. It depends. So it depends. If you do, for example, reset m out of n, there's still residual correlations. Okay. So this is actually one of our students is studying. It's quite non-trivial actually. So yeah. Yeah, absolutely. Except for m equal to 1. If you just choose only one particle and reset, they will always remain uncorrelated. Okay. But any m bigger than 1, it's actually they are correlated. Okay. So average density profile. So all you have to do, average density profile, as you know, average density is just the marginal distribution of one of the variables, right? Because you just average when you put this, so you just have to take the joint distribution. You integrate over all the n coordinates except the first one, and you set it to be x. Then this is just the average density. And in this thing you can compute easily because all these guys are inside the integral. You can integrate out all of them. They are normalizable, and so only one of them is left, and therefore you get back the answer that I showed you for one particle. So the average density is actually independent of n, unlike in the random matrix case. Here it's independent of n trivially, and this is just this double exponential distribution that I mentioned before. Okay, so the average density profile is just, there are a lot of particles near the origin, and then it exponentially decreases as you go away from the trap center, from the center. So order statistics. So now if you take a typical configuration of particles, so you can say that the mk, I want to look at the kth maximum. First maximum is here, second maximum is there, and so on. And you can set this k to be the index to be alpha n. So if alpha is of order 1, that means k is of order n. That you are counting from right side, so you are probing the bulk of your gas. And if alpha is of order 1 over n, that means k is of order 1, you are probing the edge of this configuration. Okay? So, and for simplicity, I'll just set alpha less than half, because for alpha bigger than half, there is a symmetry, and it will be minimum just becomes maximum essentially. Okay? So in this case, so I won't show you the results, I mean the details, but you can compute both in the bulk and at the edge. So typically what you find is that the location of the rightmost particle, typical position is square root of log n, okay? And the gap typically in the bulk is 1 over n, okay? And this is the width of the average density profile. So this guy, the kth maximum, probability that it takes the value w, it has a scaling form, some function of w over lambda alpha, and this lambda alpha goes like, in the bulk it's of order 1, it goes like inverse error of complementary function of this alpha. Whereas at the edge, same scaling form holds, exactly same scaling function, unlike in the random matrix theory. Here it's exactly same scaling function, except that the length scale ln is now square root of log n here. So as the n increases, this guy, very slowly, its rightmost particle position increases. And the scaling function is actually very simple. It just turns out to be 2z e to the power minus z square. Okay? And it's universal in the sense it does not depend on this k or alpha, same in the bulk as well as in the edge. Okay? And so this is this picture, is this simulation. You can see it matches very well for different values of n and alpha. It's completely universal. And it's given by a very, very simple form. Okay? So this is the order statistics. You can then ask for the gap or the spacing statistics. As I said, again, in the bulk, the gap is typically of order, if I set k equal to alpha n, actually it should be opposite actually. So this should be bulk. This guy is of, alpha order 1 is the bulk and alpha order n is edge. And so what happens here, exactly same story. So the probability that the gap between the kth and k plus 1th particle is g satisfies this scaling function here, where the scale, typically scale is of order 1 over n if you are in the bulk, and the scale is of order 1 over square root of log n. So it becomes sparse and sparse as you go away from the center. So they are, they're sparsely populated there, with the distance between them is 1 over square root of log n. But the scaling function, h gap of z, this is somewhat non-trivial. I mean, it has this function, and this is completely universal again, okay, independent of alpha. And if you look at this asymptotic behavior, it goes to constant root pi as z goes to 0, and it decays as a stretched exponential minus z to the power 2/3 as z goes to infinity. So this is again different from the usual random matrix. Usual random matrix, this is a Wigner-Dyson distribution which goes to 0 because the eigenvalues repel each other. And here, the particles actually attract each other because of this simultaneous resetting. As a result, the probability that the gap is 0 actually is a constant, it's not 0. Okay? And this is the scaling function. Again, the numerics works very well. You can ask for the full counting statistics. So if you look at the total number of particles in an interval minus L to plus L, and this is a random variable, and you can ask what is its distribution, okay, in the stationary state. So again, I'm not showing you the details. You can write this in the scaling form, 1 over n into some function of nl over n. So nl over n is the fraction of particles inside your box minus L to plus L. So this is kappa, which lies between 0 and 1. Okay? And this is highly non-trivial here. Okay, there's an explicit form where uk is inverse error function of this kappa, and you can plot it, and there's a parameter gamma, which is RL square over 4D. Now, when you plot this function, you see this very highly non-monotonic behavior of this scaling function. Okay? This h of kappa. Kappa is going from 0 to 1. So when kappa goes to 0, it has an essential singularity here. It's a very, very rare event. On the other hand, when kappa goes to 1, so all the particles, and kappa goes to 1 means what's the probability that all the particles are inside this interval L? And this has a high probability. I mean, the scaling function diverges, but it's integrable. It's a probability density. It's still integrable, and it has this, barely, integrable basically. And so it's a very highly non-trivial, behavior for the full counting statistics. Okay. So these are the sort of results which were derived in this paper. So then you can generalize this. You can say that, okay, instead of diffusing particles, I can take any particles. All I need to know is the bare propagator of these particles for a single particle, and you just have to then do this integral. Okay? So you can take, for example, ballistic motion. You can take Levy flights. I mean, you can do whatever you want. Okay? So there's a whole class of sort of strongly correlated stationary state that you can generate in a non-equilibrium stationary state. And so this is a kind of new application of this stochastic resetting, if you like. Okay? So let me summarize so far. So essentially, I started with this box problem, L1 to L2 with rate R1 to rate R2. And then I looked at one particular limiting case when L1 equal to 0, L2 goes to infinity, R1 equal to infinity, and R2 equal to R. So in this limit, becomes a stochastic resetting of n independent Brownian motions to the origin, simultaneous resetting. And this limiting case is exactly solvable with a strongly correlatedness. And the stationary joint distribution in the stationary state has this conditionally independent and identically distributed structure, which allows us to compute several physical observables explicitly. And so you can ask, how generic is this CIID structure? Okay, if I go away from, for example, if I look at the general problem of L1, L2 with the arbitrary R1 and R2, does this, the CIID structure still hold in the stationary state or not? So this is a, difficult question. We still have not been able to solve this problem analytically yet. And Una has done some nice simulations, and we see some interesting features, but we have not, this is ongoing work, essentially. But, so we cannot solve this problem, but what I want to do in the next 10 minutes is to look at a cousin of this problem. This is the switching harmonic trap. Okay, so this is a cousin of the box problem. So the setting here is very simple again. So instead of box switching between two values, I take a harmonic potential with stiffness mu, and this mu stiffness, it switches between two values, mu1 and mu2. It goes with rate R1 from mu1 to mu2. Mu1 is bigger than mu2, and with rate R2 goes from mu2 to mu2. This is, morally, this is very similar to the box problem. I mean, you can think of 1 over square root of mu as your effective confining length, and so you are effectively changing the confining length from, let's say, L1 to L2. And this mu of t, this stiffness, it changes again dichotomously between two values. So essentially the problem you are looking at, n independent particles, dxi dt, is minus mu of t xi, so Ornstein-Uhlenbeck process, plus independent noises. And this stiffness, mu of t, is undergoing a dichotomous telegraphic process, telegraphic noise, with parameters R1 and R2. Exponential distribution. So that's the problem. Okay. So as I said, morally it's similar to the box problem, but the nice thing is that this problem you can actually solve it explicitly, and the what we are interested again, that in the long time limit the system actually goes into a stationary state, and I want to compute the joint distribution of the particles in the stationary state. So this was the work with Manos and Biloli and Gregory, of course. So how do we solve this problem? Okay, so of course here, unlike the limiting case where there was a renewal picture, here there is no renewal picture. Okay, renewal things doesn't work because as you go from one phase to another phase, the process does not, when it switches, you don't go back to the same initial configuration. Okay, so there is no renewal picture here. So you have to solve by some other way the stationary distribution. So how to solve this? So basically, and in particular, in this limit, as I said, this is the simultaneous resetting limit that we already discussed. Here the renewal picture holds, but general mu1, mu2, there is no renewal picture. Okay, so how do you solve this? So I'll not go in through the details, but just to outline. So essentially, you define P of subscript 1, 2 x vector t. So this is joint distribution with stiffness in state 1 and with stiffness in state 2. And then you can actually write a coupled Fokker-Planck equation between this P1 and P2, okay, which looks like this. And it's very simple. So there's a diffusion term, then there's a drift term because of the potential, and then with rate R1, you are going away from mu1, and with rate R2, you are coming back from P2, R2 to R1, and this similarly for P2. And you start from this initial configuration. And then you want to just solve these equations, okay? So these equations actually you can solve explicitly. Best is to solve in the Fourier space. So if you go define the Fourier transform, and then you find that actually the Fourier transform depends only on the magnitude of k, which is the square root of k1 square plus k2 square plus kn square for n particles. And this is the explicit solution in the stationary state. Okay, I'm not showing you the details. But you can actually explicitly write down the solution in terms of some hypergeometric function. Don't pay too much details about the exact structure of these things, but just to show you this is the structure. Okay. So looking at this, and then you have to add these two guys to get this full stationary distribution. There's these parameters R1 and capital R1 and R2, which are the dimensionless rates and stiffnesses. So looking at this, you don't see any CIID structure, right? I mean, this is all the particles. They are completely correlated through this k square, which appears here and here. So it's not evident if it has a CIID structure or not. Okay, but so for that you need to really invert to the Fourier transform and go into the real space and then investigate basically. Okay, so it's not manifest, but it turns out that, and this was one of those instances when you actually realize that some books like Gradstein, Isaac, or Abramowitz taken can be very useful. So this function here has a very nice integral representation. Okay, I don't you can find this in the book standard. Okay, so this means this chi you can write down as some integral times e to the power minus ck square u. But once you have that, then you can easily invert the Fourier transform, because k square just breaks up into k1 square plus k2 square, and you can invert the Fourier transform inside this integral. And then you can actually write in the real space the joint distribution of particles. Okay? And if you write in the real space, what you find, indeed, that the joint distribution again has the same CIID structure. So there is this Gaussian here, where this VU has this form. So this is like an effective, inverse stiffness that the particle fills, and then you have this HU, which is drawn from the A is some constant here, which normalizes this distribution. Okay. So it's highly non-trivial, and this parameter R1 and R2 are just dimensionless rates, R1 over mu1, R2 over mu2. Okay. So this is a highly non-trivial distribution with this parameter U, which is actually uniform distribution over 0 and, I mean, not uniform, with this non-trivial distribution H of U between 0 and 1. But the structure is similar again. Again, you have this non-trivial product structure here, but then it's getting modulated by this distribution of HU. And it's not completely obvious, because this is a hidden, I call it a hidden structure, because you don't really see, physically you don't see what is U. I mean, roughly speaking, you can say U is roughly the time, heuristically, it's the time spent in potential mu2, and 1 minus U is the time spent in potential, fraction of time spent in potential U1. And that fraction of time has this non-trivial distribution essentially. Okay? But once you have this, then you can actually compute everything explicitly. And so what I'm trying to say is that, it's not always manifest, this CIID structure. You have to work a little bit, and then you find that you can compute everything. Because once you have this structure, you can again compute everything explicitly using the IID nature and then averaging over HO. Okay? So I'll just give you one example of this result. So for example, if I look at the position of the rightmost particle, it has a scaling form, 1 over square root of log n. The typical scaling is again square root of log n into some non-trivial function here. And this scaling function is highly non-trivial. So first of all, it has a finite support. It's from R1 to R2, square root of R1 to square root of R2. Now, I have not seen too many extreme value distributions where which has a finite support. For example, if you take Tracy-Widom distribution, it has an infinite support. But this is actually supported over a finite region in space. And moreover, you can tune by tuning these parameters. They depend continuously, these exponents. So the edge behavior of these things you can actually tune. And so this is one of the rare examples of a very strongly correlated system for which you can calculate the extreme value statistics. Okay? So for example, by tuning these R1 and R2, you can get the distribution, you can get the distribution either vanish on both ends if R1 is bigger than 1 and R2 is bigger than 1, or diverge one side and vanish on the other side, or diverge on both sides. So you can actually change the shape of your distribution by tuning these two parameters here. And again, the scaling function is universal. That is, it is same for all ordered statistics. I mean, not just the first maximum, but and also it turns out that this is the same for super universal. That is, it's true also for d bigger than 1. All right, so this was a prediction, for example, one of the predictions. And then, so now I want to show you that the verification of this result in this experiment, which was done by the group of Sergio Siliberto. So what he did is that, so he takes these optical traps and he puts the particles. Now, it turns out that technically, experimentally, it's very difficult to put many non-interacting particles in the same trap. So what he does, he puts one particle in, so he creates, for example, 4 traps here, okay? And each trap has a single particle, okay? And then you you change from mu1 to mu2 synchronously for all the traps, okay? So that effectively mimics the model, except the reason for doing this experiment was that in real systems, these colloidal particles, they are inside a fluid, and because of this surrounding fluid, they have hydrodynamic interaction between them. Okay, and this is long range typically. Okay. So of course, in our theory, we don't have any interaction between the particles. They're getting correlated due to dynamical emergent correlation, but there is no inherent interaction between the particles. But in the real system, there is long range hydrodynamic interaction. So we wanted to see how this hydrodynamic interaction change the prediction from the theory where this hydrodynamic interaction was not there. And so he did this experiment, and up to n equal to 8 particles, and he computes exactly this correlation function that we had computed in the theory. Okay, we just normalized by this guy here. And you plot this correlation function as a function of this. So here mu1, mu2 are just k1, k2. So you fix k1 and you vary k2 and just observe this correlation function as a function of k2. And our theoretical prediction was this formula here. And what you see is that somehow the experimental results for 2 different values of parameters, they match perfectly well with the theory. Okay, even though the experimental system actually has hydrodynamic correlations. Okay, and this is, you can see in this distribution of M1 that I mentioned, the rightmost particle distribution. So so you measured this distribution, this PDF for different parameter values, and you see a perfect match between the theory, because you can calculate for arbitrary n, not just for large n, and you can actually compare with the experiments, and it works perfectly well. So what it tells us, and this is what was surprising, that the emergent correlations which come because of this, synchronous switching of this, sorry, spelling mistake here, synchronous switching of these traps, they actually overwhelm the hydrodynamic interaction. Hydrodynamic interactions are there, you cannot get rid of them. Okay, they are there, but these dynamical emergent correlations are much stronger than the hydrodynamic interaction, and as a result, you see, the theoretical prediction for non-interacting particles actually still remain valid. Okay? So my time is getting up, so I'll just very quickly say that there are other models where the same CIAD structure comes up. So for example, you can take these n particles in a trap, and instead of modulating the trap simultaneously, I mean, you can actually take the center of the trap and just drive stochastically. So then again, you have a CIAD structure in the stationary state. So this is a joint work with Sanjib. And then you can play around with different way of driving, diffusing diffusivity, and so then again you have a joint distribution which factorizes according to this, I mean, which has this CIAD structure. You can play with the distribution, as I mentioned, that instead of exponential distribution between two subsequent resettings, if you choose any distribution, okay, so you can actually still calculate the stationary state. And you can see that, if you, except for the sharp restart case, any other case, you will have this non-emergent, these dynamical emergent correlations. So this was work done with my current graduate student, Gabriele Di Mauro. And also you can extend it to quantum models. So you can take any interacting bosons, for example, evolving unitarily in a harmonic trap between two resettings. And then after that, you do some quantum resetting. That means you project this state to the initial state. And you can again find that, that a stationary state emerges with non-trivial correlations between them. So all these problems have this CIID structure, which is very nice because this actually allows us to have a whole family of solvable, strongly correlated gas, classical or quantum, for which you can calculate several observables explicitly. And okay, this is not really directly related to this, but you can also, for this n-particle simultaneous resetting, you can also look at the first passage properties. So this is what was mentioned by Samrita for n equal to 1, but you can do it for arbitrary n. So for Poissonian resetting case, this was actually studied with Marco and Gregory. And more recently, we did the threshold resetting when, the resetting actually is event-driven things. When resetting occurs, simultaneous resetting occurs when all the particles hit a certain level. And this is the work done with Arnav Pal, who is here, and Arup Bisha is a student. This is a very recent work. And you see many interesting behaviors which I'm not going to talk about today. So let me just summarize and conclude. So main point, as I said, that you have a shared common environment. You don't need any interaction between the particles. Non-interacting particles under this shared fluctuating environment, they go into a strongly correlated non-equilibrium stationary state. And there are several examples I discussed. And this strongly correlated state actually has a nice CIID structure, conditionally independent identically distributed structure, which allows us to calculate several observables explicitly. And you can compare with experiments. And as I said, you can easily generalize to other problems. You can take any particle motion that you like. They don't have to be diffusive. You can take Levy flights, ballistic particles. I mean, many other problems. So this, it sort of opens up a Pandora's box of solvable models, which is very nice. Okay, they all have this nice CID structure. And so let me acknowledge my collaborators. So Marco, as I mentioned, was a PhD student, and he's now gone for postdoc to University of Chicago. Arup was a student of Arnav. Sergio is the experimentalist from ENS Lyon. Manus, everybody knows, he's here. Hernan is from UNAM, Mexico. Gabriel is the current PhD student. Nikhil is a student of Sanjib, here at RRI. Arnav, of course, who is here. Sanjib and Gregory. And then, of course, my earlier work with stochastic resetting with Martin Evans, and also ongoing work with Urna Basu. And I'll just finish with one slide, which is just because, I was asked to publicize for JFISE as its chief, editor-in-chief, because, so, I mean, of course, the senior people in the audience, they know about JFISE. They've all published there. But the junior people who have not published in JFISE, I mean, this is a message for you guys, that this is, this is not a flashy journal with a high impact index where you have to pay to publish your paper, but this is a solid journal where the referees do read the paper and make useful criticisms or comments. So if you have not published there, please consider, or encourage your students and colleagues to publish in JFISE. Okay, thank you very much for your. I'm sorry, I exceeded the time a little
talk.
bit.
I mean, time is actually running, so maybe if I may propose to sort
Sure, we
of
can discuss
switch the discussion,
Yeah.
I mean, to the coffee break. I think that would be most useful. And so thank you very much again for this talk.